Hello everyone and welcome back. In the previous videos we learned the fundamentals of modeling in SpaceClaim and how to prepare geometry for simulation. Now in this video we are going to build a simple real-world example, a bolted plate connection, and perform a basic structure analysis in ANSYS to evaluate the stresses in the model. The model will consist of two circular plates connected using bolts. So we will create a geometry in SpaceClaim and transfer it later on into ANSYS Mechanical and apply loads and boundary conditions, then finally review the stress analysis or stress results. So first of all, we create the circular plate. Let's create first the first plate, and this by going into design. We click on the sketch mode. Let's choose the y-axis and the plan view. Now I will go to circle. I will sketch a circle with, for example, like 60 millimeter as diameter. Now we have to exit the sketch by clicking on the 3D mode. And we got the following circular surface. Now in SpaceClaim, and as we learned before, we can use the pull feature to extrude this circular surface, and let's extrude it with 5 millimeter. We click on it and write 5 millimeter, then hit enter. As you can see now, we have the circular plate, as you can see, and it's with a 60 millimeter diameter and 5 millimeter at thickness. Now let's draw the holes in this plate, which is the bolt hole for us to be later like the full assembly. And I will create like 4 bolt holes. So let's click on this top surface and again plan view. I will go again to circle and draw a circle at a position on this line, and let's do it, for example, like 8 millimeter, and I will exit the sketch by clicking on the 3D mode. Now let's do it like a little bit professional here, so let's position it right first. I will click on this surface, click on move. I will click on this axis and go to the ruler and tell him that from the center of this small circle to the center of the bigger circle should be 20 millimeter. So as you can see now, the surface is 20 millimeter away from the center. We will go and click on the 3D mode, and as you can see, we have this circular trim on the top surface. Now let's create the hole, and this is by clicking on that surface. I will go to pull and click cut, and let's go through the thickness downward. As you can see now, we have this hole with 8 millimeter as diameter, and it was 20 millimeter away from the center. Now we can create the other 3 holes on the plate with the same like strategy, but we can do it like more efficiently and faster by using the pattern feature in SpaceClaim. And as we learned before, we click on the surface we want to make the pattern. I will go to the circular pattern and choose the axis at which the circular pattern will be created. So I will click on it. As you can see, you can like write here the number of circles that you want. Let's do it 4 in this example, and I will click on apply. As you can see now, we got like automatically the 4 holes on this plate. Now in order to delete the pattern, let's delete the pattern, so no at this location, so it will be independent and we can use the plate whenever we want or adjust whenever we want. So let's do or copy this plate and do the another plate on top of it with the same holes. So we already draw the first plate, we can now click on this plate 3 times on the screen, or you can like choose it directly from the structure tree by clicking on the solid part. And let's click on Ctrl C, then Ctrl V, so which is copy paste, and as you can see we have now the other part. And we have actually to move this part along to be in contact to the top surface. We already did the downward plate with a 5 mm as a thickness, so I have to move the second plate 5 mm upward. And we can use the move tool by clicking on the axis, vertical axis, and right 5 mm, then hit enter. As you can see now, we have the second plate, which is have the same holes as you can see at this location. Now, and we already know that we will do like a small analysis, structure analysis on this like 2-plate assembly. And in order to do this, we have to define a support and like a load on the top face. But in order to do this like in a realistic way, let's trim a circular form on the middle of the bigger circle, where we will define the load or support at the downward or bottom face. So let's click on sketch again on the top face here and plan view. We click now on the circular form and let's make a circle of 20 mm diameter. And now we go to design and click on 3D mode. As you can see now, we have this trim face. We will define the force at it vertically up, and we still have to define or create a circle on the bottom surface where we will like fix this plate. This will be more realistic than fixing the whole plate actually. So in order to do the second circle, we can do the same as we did like before, like click on sketch on this face and sketch the circular form, or we can project this face, and as we learned before, we can choose this face and go to the project feature here, and we can click on the select target face. We rotate the view and tell him that I want the marked surface to be projected into this surface. As you can see, we have this trim now, and we have to click on apply to get it. As you can see now, we have this surface at this location. So for this connection, it's ready for defining the boundary conditions. We already have the bolt holes, but now we still have to model the bolt itself. So first of all, we have like multiple options to draw the bolts. We can draw it as a solid. We can draw it like with an efficient way, like modeling them as beams. And in this video, we'll see like later how to define this beam also in ANSYS mechanical, so we can get later on the axial force acting on this bolt and the shear force, like without modeling the bolts as a solid, and like make a lot of like elements and nodes in our system, which is like take a longer time to calculate or do the simulation at the end, and we will get actually the same result even when we modeling them as beams. So let's do them as beams. In order to do this, we can go to sketch. I will go to this surface and click on plan view. We go to the point, as you can see, and we click at the center of each circle that we have here. As you can see now, we click on them, and now we have these 4 points. We go exit now. We click on 3D mode, and as you can see, we have these 4 points. Now from the structure tree, I will go to curves. I will mark all these 4 points and click on pull. Now the direction of pull, it's upward. That's what we want actually. In case it was not the case in your by you, sometime it will be like tangent to the surface. So to choose the direction at which the pull will work, actually you will go to this like pull direction there option, click on it, and for example I will choose this cylindrical form, so he will make sure that it will be like in the center of this cylindrical form. So I will go to this up to function and tell him that these 4 points will go downward until this edge. As you can see right now, we have these 4 lines on the middle of each bolt hole that we already drew here. So now we have to convert this line to beams to model the actual bolt actually. And because we already modeled a bolt hole here with 4 millimeter diameter, so I will assume, or let's do here M8 bolt. And in order to do M8 bolt, let's do a cross-sectional area of this 8 ball of 3.25 millimeter. So in order to do this, let's go to prepare. We click on profiles and on this circular form. Now after clicking on it, we will get something called beam profiles in the structure tree. I will open it. And as you can see, it's named circle. Let's name it here M8. We right click on it and edit beam profile. And from here we can go to design. We click on pull, and instead of this 10 millimeter radius, let's adjust it to 3.25, which is the cross-sectional area actually for the M8 bolts. So we are finished right now. We click on this X, we go out, and then I will go back to structure. And as you know, we have already the M8 here at this location. And we can use this actually again. So in order to do this, I'm gonna to check something first for the bolt connections. Actually for the bolt 33, actually it should actually bigger the size of this bolt, but let's make sure how it should be. So this should be actually around, okay, it should be around 3.41. So let's adjust it again in case you make an error with modeling the cross-sectional area of this bolt. We go back to edit beams profile. I will go to pull again and choose, instead of 3.25, it's actually 3.41 exactly. So this is the actual cross-sectional area. We go back now to structure tree, and now I choose all 4 lines. I will click on the prepare function, and from this profile, we already drew the profile M8 here, so I click on it, and now we got 4 beams with the M8 cross-sectional area. So our model now is almost finished. We must only do the area at which the bolt will be mounted, which is the under bolt head. And in order to do this, let's make a cross section, like a small surface around the bolt hole here, and we can go to sketch mode again. And for M8 bolt, let's make a 12 millimeter as a diameter, as it will be the under bolt head, of course with using the washers for this bolt size. And let's draw the 4 circular form for each hole by clicking on the center and 12 millimeter each circle here. And I will now, we got the trims, but actually we have these extra faces and we delete them. We can mark all the 4 of them, or just click on this surface and delete. Now we have these faces at which the beam will be connecting to this surface. Actually down it will not be the same. I will consider that this will be a thread for us. So this vertices here at this location, it will be connecting to this face, and it will be described as the bolt comes in thread here in this plate. So for now this is enough and ready to be simulated on ANSYS mechanical. And now Actually, after finishing the bolt holes modeling and the plates and defining the beams, we are allowed to transfer the model to ANSYS. And in order to do this and to prepare the structure analysis setup, we just go back to the workbench schematic and we click like 2 times on this model and click on yes. Now he will open the model and update the model by transferring the model into ANSYS Mechanical, as you can see now, and he is like almost finished. He will take a little bit until he's imported the file. And now on our screen, as you can see, we got the model that we already like draw in Space Claim. So now let's describe or explain how to set up this model and solve it and show the results at the end. So for this plate, we go first to the geometry. In case we want to like to define like a specific material, we can like add a material or use another material from the material section here other than structural steel, but in my case right now I will use a structural steel. I already changed the A modulus to 210 gigapascal. You can do this actually by going to the workbench schematic. You can click 2 times in engineering data, and from the engineering data here, when we have the structural steel, we can change the Young's modulus to 210, which is the exact A modulus for the structural steel. We can, after finishing or adjusting the A modulus, Young's modulus, we can go out and we can update again the model. So in this case, our 2 plates and the beam are with the Young's modulus of 210 gigapascal, and this is what we want. Now I will go to the connection, and as you know, we have 2 plates, so we have to define a frictional contact between these 2 plates. So I create a contact, I will click on it, and instead of bonded, it should be like frictional. Usually it will be taken like a 0.12 as a frictional coefficient between steel plate and 2 steel plates. And I will change the interface treatment from add offset no ramping to adjust to touch. So now we have like prepared the contact. Now let's hide this part by clicking on it and go to hide body. I will choose this face and click it as a contact. Now I will right click on my mouse and invert visibility, so we get the other part, and we can define the target face here as target, and then we can click again and show all bodies. So as you can see right now, we can see like from the right side in this small windows that we have the contact face on the top or under face of the top plate and a target on the top face of the bottom plate. So now we define the contact. Now we have to like make a joint for each beam connecting to the plate, and in order to do this, also from the connection group, we click on it, insert, and a joint. Actually we must not change anything on the settings for this joint. We need after all 4 joint on the top and for another 4 joint for the bottom actually, so we need like 8 joint in total. Because we don't have like too much joint, we will do it manually in this case later on, and in other video when we have like a lot of bolts, we can do it like efficiently and more like and faster. So I will explain how to do this through the automation feature in Mechanic or ANSYS Mechanical. For now, let's do it manually just to learn it. And I have 1 joint. First of all, I will duplicate it, and I will click on both of them and duplicate it again, and I will choose the 4 and duplicate them also again. So we have now 4 joint. Now I will choose the first one I will go to the point selection up and I will choose this vertex and click on the scope, which is to reference, and I will go to the face selection and choose this face and choose it as the mobile scope here. So as you know, right now we have like the joint or this beam, which is will be connecting through this vertex to this face, with a top face of this plate. Now we do the same for all the 4 beams. We choose a point, surface, and choose this again. The third one, also the face, the 4 beam, and this face. Now we go and rotate the view down, and now the difference is that this vertex will be mounted to the inner-like surface of this cylindrical form, which is the thread in our case. So I will click on them there. This vertex to the surface, and the other one the same. So now if we click on all the beam, as you can see right now, the bolt will be defined like this. Like we already defined now the joints and the contacts. Now we are ready to generate the mesh. In order to do this, we click on the mesh. From the element order, let's choose quadratic. And for the size that we have, let's start with 5 mm actually. And in the sizing section, we can do the following. Actually, I would recommend to adjust this to no. And let's capture curvature here. Let's like turn it on. And tell him that the minimum size, let's do it like 2 mm for example, and instead of 70 degree here, let's do it like 45. And he will do automatically the mesh, so when he will see like circular forms, he will try to maintain these like settings here what we are defines. Of course we can define manually exactly how much the size at this faces and so on. So let's see first how the automatic mesh will be. So I will go to mesh and I will click on generate mesh. This is small model, so it should be like fast. So as you can see right now, that this mesh, it's not so fine actually, but it could be like better for sure. So in this case, I will use the following. I can first hide the beams. I will go to right click, hide, and line bodies. So we only have these 2 solid parts. I click on this axis, and let's change the mode of selection from single select to box select and on faces. And let's mark everything here from the right to the from the left to the right. So now we are choosing the top face plus the 2 face here. Let's choose also the other ones by clicking on Ctrl all the time. And now we marked all these faces. Now I go to mesh, right click, insert, and sizing. And let's choose actually here 1 mm. And after this, let's generate again the mesh. And as you can see right now, our mesh, it's way better than before on the area where we'll join it. Actually, the plates are also like could be like better. So let's change the element size on that general like mesh from 5 to 3 mm. So I click on it and generate again. This will help like that the contact will work better on our case. Now it's like much better than before actually. And let's right click and show all bodies. As you can see right now, we have not so much like elements in the beams. When you are modeling the bolts through a beams, you must like define like as a like not so much element in the beam, but when you have like not so, you have like some elements, like 4 elements, 5 elements, this could be like a problem while ANSYS like calculate the model. And you might get like a problem with the conversions. So in order to prevent this and get like accurate results, I will recommend also to like increase the number of elements on these beams. In order to do this, you can go back to the selection mode. You can change this to single select and click on edge. I will click this beam. I will click also on control all the time and click the second one and the third one and the fourth one. I will go back to mesh, right click, insert and sizing. Now from sizing, I will change the type from element size to number of divisions. That's mean the how much division I want on these beams. So the beam now it's like 10 millimeter in length, because the two plates are 5 millimeter thickness each, so they are 10. So let's make element each like 1 millimeter. So this by dividing or choosing a number division of 10. And now as you can see, he shows you like how much the elements are, and it seems like enough for our case now. So this is enough. I will refresh again the mesh, and now it's actually way better, as you can see. Okay, so like this we finished the mesh, and now we are ready to prepare the setup, which is the boundary conditions. For now, from the static structural, I will go to it and right click, insert, and choose like fixed support. I will rotate it like the view and choose this surface as my fixed support face. And now let's right click again and choose a force. I will choose this top face again and click on apply. Let's change the defined by from vector to component, so we have the x, y, z. And let's pull or like define a load on this face upward with, for example, let's try 1000 Newton. So now we are pulling this plate from this surface 1000 Newton up. So now we define the boundary conditions. Actually, we already have this beam connecting through this face, and the thread down through that joint were already like defined, but we should also define the bolt pretension, because now the bolt pretension is 0 since we didn't define anything. So we must have like a bolt pretension. In order to do this, from the static structural, I will right click and I will choose bolt pretension. We already have like 4 bolts, so I have to create 4 bolt pretension. But first of all, in order to model the bolts, we have to define 2 steps in our analysis. In the first step, we have to define the bolt pretension. Then in the next step, we start to define our loads. So I go back to analysis settings and I will choose number of step 2, and we can like change the auto time stepping from program control to on. I will go back to current step number, click on it and change it also to on. Now I go back to force because we like change the number of steps. Now I will go and click on these cells and copy and paste. And in the first step, I should have nothing, because in this step we should have like only bolt pretension. So I will click here 0. So now the force is ready. I will go back to the bolt pretension. And for the M8 ball that we already like used, we have and according to like VDE, which is like actually according to norms, how much bolt pretension can this bolt like withstand. It's actually for the strength class of 8.8 around like 18.6 like kilonewton. But in our case, like I will define like a little bit like a smaller like bolt pretension. So I will choose instead like 10,000 kilonewton as a bolt pretension. So in the first step, we are at like 10,000 newton, and in the second step, we have to lock this bolt pretension. So the first one is ready, but it's still missing. It's not defining right now to anything in the model. Before we define this bolt pretension to each edge here, let's create for one with the same settings. So we create duplicate. We have the same settings as before. We don't have like to do this again the same and take so much time. So we can simply duplicate this, and I will choose this both and duplicate them. Also, we have now 4 bolt pretension. Now I go to bolt pretension 1 here. I will go to edge and choose this bolt, and in the geometry here apply. So now we have bolt pretension on this beam. I will go to the second one and the same. I choose the beam, apply, and then the third also here apply, and the fourth bolt pretension for the fourth bolt here also apply. So now we define, if we click on the static structure, we have the bolt pretension on the 4 bolts. We have a load here with 1000 newton upward, and we have a fixed support on this circular face down. Now we defined our materials already defined, the connections, contact and joint are already defined, the mesh it's already ready, and the boundary conditions now are defined. So we are ready to solve the model, and let's now solve the analysis. So we go to the solution, and from the solution, and in order to get like information about the bolt, it's like recommended to turn on some like features, which is, you will go to analysis settings. I will go to output controls, and let's change the nodal forces here from no to yes. This is important to get like nodal forces later on. And I will go to the solution. Also, because we already have a beams here, we can like change the beam section results from no to yes, so we can see like, or we have the option to see the stresses on the beam later on. So we can click this. Right now we can right click on it and hit solve. Now ANSYS, he will solve the model, and once the solution is complete, we can like review the stress distribution first on this like 2 plates, and also we will see like where our stresses will be located on our model. Later on in the next video, I will like explain to you exactly how to do the assessment of this bolt, if they are okay or not according to the VDE 2230. For now, let's see only the stress distribution on the 2 plates, like a little bit the axial force acting on the beams and the shear force acting on the beams. For now, the model is almost like finished, so let's wait a little bit. You can like actually see the convergence by clicking on the solution information, and from there you can go to the solve and go to the force convergence. From here you can see how the convergence look like. The first step, which is the bolt pretension, it's already like finished with the 3 iteration, and now he is like almost like reached the criterion, and he almost like done. As you can see, our model is already calculated. Now we are ready to see the results. I recommend every time you solve a model and before you see the results to go back to the workbench schematic and save everything by clicking on Save Project. we click on them so we can make save that the results are already saved on the like document path. So we go back after you finish, we go back to the model and we click on the solution and insert first from the deformation, like total deformation, and let's also click on the stresses, like equivalent von Mises stresses. Now we click on the solution and evaluate our results. Now we click on the total deformation. As you can see, we can see the deformation. Okay, we have like a too small like deformation, as you can see, a millimeter, like 0.009 millimeter. We can exaggerate like the way he like show us the deformations by going to result and by changing the true scale here from 1 to like the automatic one. Let's do the second one, and then you can see like what will happen on the middle. Actually, we can do a section in this plate. I will explain this also on the next videos, so you can see like in details how this will deformed, and this tool is like important for in some cases. For now, let's like re-choose again the one true scale. We can like hide the elements here from going to edges and click on no wireframe. So we only see the deformation now on the model. We can go back to the equivalent stresses, and now we are seeing the stresses on our model. As you can see, we have stresses exactly under the bolt head, which the beams are connecting. So let's like adjust our scale here from 363 to 235, and as you can see now, the automatic, let's like change it again just to see the stresses. And as you can see now, I will hit like probe, and on this phase we are expecting to have like 21 megapascal, which is not too high actually. It's almost okay. And near the bolt head, which is like logic to get these stresses because of our like bolt pretension. So in general, the stresses are okay on the two plates. You are seeing the 409 megapascal. In order to see like where these stresses are, if they are like singularity or whatever, we can go to up to the results and click on maximum. And as you can see here, the maximum is hitting at some location here, and it's mainly actually like through singularity. In order to make sure, we can go back to geometry. I will click on this. I will hide the bottom plate first. Let's see this. So the stresses we are seeing on the hull at this location, they are actually important to see, and we are expecting like 145 megapascal, which is still okay for if we are using the material S2035. And if we click invert visibility, so we are seeing the stress on this location. This is like actually expected, because it's like the thread and the bolt, and because we already defined a bolt pretension, the first thread will get like higher stresses. Also another reason why we get like higher stresses on this like region, it's actually because of the contact, and because like you might have like a small penetration at these locations. But for now it's like okay. I will like select this. First of all, for detailed like evaluation, we can like also explain this in another video. For now, we already saw the total deformation on our model, the stresses on the plate, also from the around here, like about 25 megapascal. Now, how to see the axial force on the bolts and the shear force. From the solution, you go there and you go to the beam results and click on axial force. We go again to solution, insert, beam results, and click on shear force. Now we click again on solution and evaluate our results. We click on axial force, and now as you can see on the screen, we are seeing like how much axial force acting on each beam. And as you can see right now, the forces actually is not too much, because we already have like 1000 Newton which will be distributed on these 4 bolts, but the bolts are already like under bolt pretension. So the force that you are seeing right here is including the bolt pretension. In order to see the force acting as external forces, you have to duplicate this analysis and suppress the bolt pretension. Then you will get the extra force that this will be acted on the bolts we have. So you can use it later on to do the assessment according to FAUDE E2230. But for now, and depending on these values actually, and because we are not moving away from the bolt pretension, it's most likely like the bolts are okay, first of all. Second, you can make sure from the equivalent stresses, you are seeing maximum on this bolt actually, that if we go back to geometry and choose all these beams and click on solution, and click on equivalent stresses and retrieve this results. As you can see, as a maximum stress on this bolt, you have 276 megapascal, which is okay for the bolt used here. And after, like we already say, like they are like out of 8.8 as a strength class, and these stresses are like under the limits for sure. So now to see the shear force acting on each bolt, you click on the shear force and you can see the maximum shear force. The forces here actually are not too much. We have like 7 Newton here, 5 Newton, and this is too low for the bolt side that we already used in this model, or under the load that we have. Of course, if you make the load higher, the bolt will be like under like more like overloaded maybe if the force is too much. And depending on the results, you can see if the M8 bolt still handle this force, or you have to go with a like bigger like bolts and so on. So for now, we did explain like how to model this like two flange plate bolt connection like through this bolts, which is the way are like the M8 bolts, and we learned like how to define a simple structure analysis like in ANSYS, how to define connection, joints like beams, bolt pretension, and boundary condition in general. And yes, like this type of analysis is useful like for understanding whether the connection design like is safe, and where critical stresses like concentration occur, like as we saw already like on this whole bolt holes like at the end top, like we already saw that we have 145 megapascal, which is still okay in our case. However, like real bolt assessment involve much more than just like checking stress plots and so on. As I told you before, we can go further with this in details in another video and do the assessment according to FAUDE E2230 using the results from ANSYS. And things like preload, like friction, bolt stiffness, joint separation, and fatigue also like become important, of course, but we will talk about them like later on. In the next video, we will go like deeper into the bolt connection like assessment and discuss like how bolted joints are evaluated like according to the FAUDE E2230 guidelines. So if you found this helpful, make sure to subscribe so you don't miss the next part of the series, and feel free to have like a comment if you have any question or suggestions. Thanks for watching, and I will see you in the next video.